Good morning, ladies and gentlemen. This is Ben Keyser with Applied Flow Technology, and I'd like to thank all of you for joining us today in the webinar that I'll be doing, talking about how to account for compressible effects correctly using AFT Aero. And so there are various traditional simplified methods for handling compressible flow, and sometimes they work pretty good and sometimes they don't. And it's important to understand what the limitations to using those simplified methods are. And today I'm going to go through a couple examples of what it looks like if you were to use AFT Aero for a actual compressible system to correctly handle all the compressible effects versus if you were to use AFT Fathom using incompressible flow assumptions. So we're going to talk about that today. And before I jump into this, there's a really important technical paper on this that I want to highlight for you all. And so if you go to our website, aft.com, under the Learning Center, if you go to technical papers, this is where you can find all of our really insightful articles that we've written over the years. And the one in particular is this one right here called Gas Flow Calculations Don't Choke. This is a really important one to read. And when you get into reading that article, this will actually walk you through the fundamental thermodynamic equations that AFT Aero uses, which are really important to use to correctly handle gas piping systems. And it also goes into detail on some of the other simplified methods that are available and the shortcomings of some of them. And so I also have provided a link in the PowerPoint. And so if you want the PowerPoint, feel free to email me at benkeiser@aft.com. That is BENKEISER.com. And one more time, just to make it easy, I'll put it up on my screen. It is BENKEISER@aft.com. So I'll let you take that down for a quick second and email me, and I will send you my presentation. And that is for those of you who are listening live, as well as if you are listening into the recording of this webinar, because this webinar is being recorded. And for those of you listening live, you'll be sent a link to where you can watch the recording again later this week, or you'll be able to send it around to your friends and family and loved ones if you like, if they really want to learn about compressible flow. All right. So let's go ahead and get into this. I do have some slides here for you today, and we will be getting into the software in a little bit. And so just jumping right into it, these are the 5 fundamental thermodynamic equations that need to be solved simultaneously in order to obtain a highly accurate compressible flow solution. So you need to solve the mass balance, momentum balance, energy balance, equation of state, and the Mach number equation. And these 5 equations are heavily coupled and dependent upon each other, and that makes compressible flow nice and complicated and not straightforward. And so what I want to do really quick here is zoom forward to slide 23 here. This is some information that I've shared in the past in previous webinars talking about AFT Aero. What's so special about compressible flow? Your density changes are significant. Your velocity is no longer constant. And so all of these things need to be dealt with correctly. So with this in mind, there's a lot of slides here that go into the basics of compressible flow, possible methods of analysis. There's a couple slides on that. It points out the problems with these traditional methods, and then the approach that AFT Aero uses for handling compressible flow, which basically it is solving the 5 fundamental thermodynamic equations simultaneously, which is all of these right here. So I'm not going to spend much time today on going through these last few slides. I will leave this to you that you can read through on your own. This slide here is where I provide the link for that compressible flow article in Chemical Engineering Magazine. And that way, these slides will give you a lot of good background information. I want to focus on basically jumping into the analysis on how I'm comparing the results between Fathom and Aero. So let's get into this. How well do incompressible flow methods with Fathom compare to truly compressible flow methods in Aero? So these are the parameters that we're going to compare today: flow rates, volumetric flow rates, pressures, temperatures, and velocities for a flow path. And that flow path is going to start at the atmospheric intake, travel around this path out to this discharge room. So we're going to track how the pressure, temperature, and velocity changes in that simple single flow path. Now, regarding volumetric flow rates, this is where things get tricky and kind of confusing. And we're going to talk a little bit about the differences in volumetric flow rates here in a little bit. So we're going to look at standard cubic feet per minute, which is really a mass flow rate. The word standard or normal for the metric system, when you see the word standard or normal, that ties the volumetric quantity, cubic feet per minute, or cubic meters per hour, it ties that parameter to a specific density at a pressure and temperature at standard or normal conditions. And so really that makes the SCFM, or the normal volumetric quantities, a mass flow parameter. And so we'll get into that here in a little bit. And then in Aero, because the velocity and density is changing all throughout the system, the volumetric flow rate actually changes everywhere also. So when you're not dealing with incompressible flow, when you're looking at volumetric flow rate, that's really not a useful quantity very much because it changes. So in Aero, you're going to have a volumetric flow rate at the inlet and then a different volumetric flow rate at the outlet of each pipe. And so what I'm going to compare today is the average volumetric flow rate from the inlet to the outlet, and I'm going to compare that with the volumetric flow rate that is calculated in AFT Fathom. And so this is the system. We're taking air from the atmosphere. We are we've got a blower here where our blower is providing flow at 2 pounds per second, and we are discharging the flow into various rooms. These are all at atmospheric pressure, and so that way we'll be able to figure out what kind of flows that we're getting at each of those discharge locations. So I'm going to go ahead and jump into AFT Aero now, and I'm going to open up my model. And so let me open that here really quick. All right, so this example actually comes from one of our standard AFT Aero walkthrough tutorials. How do you find the walkthrough tutorials? Well, if you go to the help menu and then show examples and choose your desired units, this will open up the examples help file. And so the example that I'm demonstrating right here is this one, air blower sizing. And so if you worked through this example, it'll show you how to build a model of this particular system. all the input that's needed for that, and then you can run your results and calculate the answers. So that'll walk you through how to do that. So in this particular example, it has you compare a few different scenarios: adiabatic, 80% or 80% efficient, and 60% efficient. What is that efficiency dealing with? It's dealing with the blower. Okay, and so the blower, we're just doing a very simplified sizing for, a centrifugal compressor. If you did a fan with the sizing option, it would be the same thing. So if I chose fan and kept it as sizing, these are the same flow rates and efficiencies as if I was to choose a centrifugal compressor with the sizing option. So just know that there's no differences there. So all we care about right here is our flow rate and the efficiency. Now, one thing that is really important to handle in compressible flow is compression heating. Okay, so here is our compression process thermodynamics, and you can choose from a adiabatic process, polytropic, or you can determine it from efficiency of your fan or blower or compressor. And so as a really quick aside here, I do have a slide that talks about that on compression process thermodynamics, where when you are increasing the pressure of a gas, your temperature is going to go up, and it's dramatic. You're going to have a dramatic increase in temperature. So we have an adiabatic situation for a 100% efficient compressor, basically, and a non-adiabatic. So it has you look at adiabatic, 80% efficiency on the fan, 60% efficiency, and then there's, in this example, another 60% efficient compressor, but it's having you evaluate heat transfer. I'm not going to cover that scenario in today's webinar. That's something that you can look at on your own. So if you were to look at the temperatures, here's what you would be seeing is the temperatures are coming in at about 68, 70 degrees Fahrenheit coming into the fan. And when the gas is pressurized, the temperature coming out of the fan is very high, starting at 160 degrees Fahrenheit for adiabatic, 185 for 80%, and 230 for 60%. So it really racks up those temperatures out of the compressor very high. And AFT Fathom doesn't handle that whatsoever. So keep that in mind when you're dealing with compression processes of any kind. Blowers, they will increase your temperatures significantly. How much? That's the question. So I'm only really going to compare these two scenarios, the 80% and 60% efficient scenario. Now, how would I go about opening this model? How do I import my Aero model in Fathom? Because if I want to do a comparison, I've already got my Aero model or maybe my Fathom model built, and I want to open it up in the other application to compare. So here's what I would do. I'm going to go to File, Save As, and I'm going to save this as Aero Blower Sizing Comparison Webinar Demonstration. Because I already did this, but I want to show you some things that are important that you have to set up once you bring it into Fathom. So I click Save, and so this is the model that I'm going to open in Fathom. And so I'm going to go back and open the previous Aero model, which was this one. I always like to save the file with a different name before I import it. That way I can preserve a backup for myself. So here's AFT Fathom. To import an Aero model, really easy. You just go to File, Open, browse to where your model is saved. And here, this is currently only looking for AFT Fathom models. So I need to change that to all. So when I change it to all file types, this is where I can look at my model that I just renamed for webinar demonstration. And I'm going to click open. And it's saying you are trying to open a Aero 8 file in Fathom. Some data may not be able to be converted. Do you want to continue? Yes. And so keep that in mind, where the majority of your model will be brought in to the other application, but there might be some slight adjustments that you need to make. And I'm going to show you how to navigate through that. So I'm going to click on yes. And this is going to start bringing things in. When the file is saved, it's going to be saved in the file Fathom 11 format. And do I want to rename with the Fathom extension? Yes, I do. And so now it's called Air Blower Sizing Comparison Webinar Demonstration.fth for Fathom. Perfect. All right, so let's look at the 80% efficient scenario. So once you bring in your model from any AFT software into any other AFT software, whether you're going from Fathom to Impulse, Impulse to Fathom, Aero to Fathom, Fathom to Aero, any way that you skin the cat, the first thing that you're going to want to do is click on the status light in the bottom right hand corner, because this will walk you through helping you figure out what things are different. And so first things that is different, the solution control in Fathom is certainly different than AFT Aero, because in AFT Aero, I'm dealing with not only the regular tolerances like Fathom does, but it depends on what solution method that I'm using. Now, I'm not going to talk about this today, but just know that there are differences in that. Just leave it at the default parameters and you'll be fine. Okay, so here's Fathom. Next thing, specify system properties. So if I go back into Aero, here's my pink flask. That's my system properties window. It's a little bit more simple in Aero than it is in Fathom, because in Aero, all you need to do is just pick which gas you want to work with, add it to the list. You can keep the default equation of state and enthalpy model, and then click OK. And that's really all that there is to it. There's not much that you have to do for the fluid properties in Aero as you do in Fathom. So when I go back into Fathom and I click on system properties, this is where we need to define our fluid information. So the default is user specified with a density and dynamic viscosity. That's all that's required. But I want to get a little bit closer to actually using air. So how am I going to do that? I'm going to go to AFT standard, and I'm going to scroll up and I'm going to use air at 1 atmosphere. Now it also provides you air at different pressures, because as you can see, when you use air at different pressures, the thermodynamic properties are going to be different. So choosing the pressure level that you are operating at is really important. In my Aero model, I'm just taking air in from the atmosphere at 0 psig, 70 degrees Fahrenheit. So that's what I'm going to do in Fathom. So I'm going to use air at 1 atmosphere, double click it to add it to the model, and I have to put in a temperature. So my temperature, if I go back into Aero, well, in Aero, in the system properties window, you don't have to specify a temperature here. Where do you specify the temperature? Well, the place that you specify your temperature is in your boundary conditions. So this is where I'm defining the inlet temperature for the system, which is 70 degrees Fahrenheit. And then in Aero, that temperature is going to change due to the compressible effects of compressible flow. In Fathom, that's not going to happen. In Fathom, I'm going to put in 70 degrees Fahrenheit, calculate the properties, and these are the properties that are going to be used in every pipe throughout the model in Fathom. So the temperature will not change in Fathom. No heat transfer, no temperature change. Properties are going to stay exactly the same. And that is where the incompressible flow methods can start to break down. Because in reality, all those thermodynamic parameters, they are changing. Sometimes they may be significantly different when you're assuming incompressible flow. Sometimes they may not be. It's very much a case-by-case basis. So once I click that, I've got a green check mark. The next thing is to define all pipes and junctions. Well, if I brought in all of the pipes and junctions that was fully defined in Aero, what is missing in Fathom? Well, if we click on that, it says, hey, your atmospheric intake. So if I click on this and it says reservoir, it's saying to enter a pipe depth. So this is where you need to get creative and just pay attention to what you're doing. So the default junction it's going to use if you bring a Aero model into Fathom is it's going to replace it, or it's going to replace the tank junction from Aero with a reservoir junction in Fathom. And so if I open this up here, as you can see, it's asking for a liquid surface elevation and a pipe depth or elevation and a liquid surface pressure. So this does not really go directly with Aero. So if I go into Aero and I open up the tank junction, it's based upon a fluid, a pressure, and a temperature. So what I'm going to do in my Fathom model is I'm not going to use the reservoir junction. I'm going to replace it with a different kind of junction. Which one am I going to use? Well, I'm going to do this in the base scenario. And I'm going to use the assigned pressure junction, this guy right here. And so how do we change this easily? Well, whenever you hover over a junction, you'll see the tooltips that appear down below: stay active, morph, and split pipe. So I'm going to use the morph option. So I'm going to hover over the assigned pressure junction, hold the control key down, click and drag the assigned pressure junction right on top of the reservoir on the workspace and let go, and bam, it is now a assigned pressure junction. And when I open this guy up, all I need to do is put in a pressure, not 70 psi A, 0 psi G. Now, where's my temperature? Well, you don't have to specify a temperature in this case, because in Fathom, you already specified your temperature in the system properties, because again, it stays constant. I think I did not click OK when I did this. So let's see, 70 degrees Fahrenheit, calculate properties, click OK. There we go. So those are some of the things that need to be done to be able to get a good comparison, apples to apples. Another thing here is, when you're looking at the different compression thermodynamics, in Fathom, if I open up the pump junction, it is possible to specify the efficiency of the pump. So if it's adiabatic, this would be 100%, okay? But in my 80% efficient scenarios, this is where you can keep it using 80% efficient. That's going to affect the power impact of your fan in Fathom. And then we have the 60% efficient scenario right here. So that's a little rundown on how you would go about opening a AFT Aero model in Fathom, okay? Now again, I've already done that, and so I'm going to just go ahead and open up that model that I already brought in. And this is the one I'm going to open. All right. So here we go. We've got our AFT Aero model, and I'm only going to compare the 80% efficient and 60% efficient scenarios between the two models. So we can do a batch run for that. So if I go to File and then Start Batch Run, this is where you can add specific scenarios that you want to run. I already added the two scenarios and we can start the run. So that's going to do both of them one after the other. And then I'll do the same thing in Fathom. It's probably better just to let this finish. That way my windows don't get in front of each other. All right. Now, as you can see here in Aero, I'm comparing results between the two scenarios in Aero, 80% efficient and 60% efficient. How do you set up this multiple scenario formatting? Well, the way that you do it is by going to the output control window. Let me circle it for you. You can find it here or on the main toolbar, whichever one you like better. It's the same button. And I'm going to go to the multi-scenario tab. And you click selected scenarios and then select scenarios. Just pick the ones that you want to compare. And there you go. That's all there is to it. All right, so there's Aero's results. And then I'm going to do the same thing here in Fathom. Start batch run. They're already ready to go. We'll start the run there. And it's going to run both of the two scenarios. And we'll be able to compare our results. All right, so here's Fathom's results. All right, so if you wanted to, you can look at, you can do some sophisticated things where, you can hide your checklist, collapse your quick access panel, and, you can look at results side by side with each other, like this, if you really wanted to. I already took things into Excel and compared things in Excel. So you can copy the entire table and paste it into Excel, or you can copy single pieces of data if you want. There's also a really helpful Excel export manager that you can set up to export specific pieces of data. This is right now set up to export the entire pipe results table, as well as one of my profile plots for the graphs. And so that way you can use it to do exporting from the software directly into Excel. And you can tell Excel, which specific cell you want it to go into. I'm not going to go into detail on how to use the Excel exporting. If you go back to our website, aft.com, you can go to the Learning Center and then Tips and Tricks, and just do a keyword search for Excel. And when you do a keyword search for Excel, this is where you can find a whole bunch of tips and tricks articles that we've written dealing with Excel. And this is one of them, using the Excel Export Manager. So that's a really good article to read on how to set things up. All right. So I think when I did this, I think I did it kind of manually because just, when you're going on the fly and you're, trying to figure out, what data do I really want, you kind of just do things ad hoc, where using the Excel Export Manager can be a little bit more intelligent, where you pre-plan what results you want to dump in. So, all right, so here's my spreadsheet that has all the results, and let's look at the flow rates first. So here's what I did, is I took the flow rates from Fathom and Aero, and as you can see, this is comparing the, for pipe number 1, 80% efficient to 60% efficient scenarios. And then for pipe number 2, pipe number 3, pipe number 4, etc. And this looks at the mass flow rate results in Aero for both scenarios, and the mass flow rates in fathom. And then we also get into the volumetric stuff, which I'll talk about in a minute. So it's kind of messy in this format, which I was using the multi-scenario output for that. And when I was thinking about how I wanted to do my graphs, I wanted to compare the Aero flow rate and the fathom flow rate, but only for one scenario at a time. So 80% efficient, etc. So this is where I actually had to create two separate tables, where this table is the 80% efficient results for the blower, and then we have the 60% efficient results for the blower. So I already made this nicely in my PowerPoint, so I'm going to go back in here. All right, so let's take a look at our results here. So when we compare the mass flow rates for the 80% efficient scenario on the blower between fathom and Aero, you can see here, I apologize, I should have labeled my axes. I was in a hurry and I didn't do that, so sorry about that. This is pounds per second, and this is pipe number. Okay, so for pipe 1, 2, 3, etc., you can see that the mass flow rates are very similar between fathom and Aero, so that's good. Mass flow rates are going to be the same, and there are, some very slight differences that you would see, but not much. This is the same type of table, but for the 60% efficient scenario. So for the 60% efficient scenario, you can see here, mass flow rates are still virtually identical. So those happen to be the same between fathom and Aero, and this is where you might be able to get away with using fathom with incompressible flow methods if you only cared about the mass flow rates. There's other parameters that are more different from each other, and so we'll get into that. But before we do, let's do a quick discussion on volumetric flow rates and what's going on with that. So there's CFM for cubic feet per minute, ACFM, which is actual cubic feet per minute, and then SCFM, standard cubic feet per minute. So cubic feet per minute is often used for volumetric flow in industry, and this can be potentially confusing. So if you are only to use cubic feet per minute, CFM, is that talking about actual cubic feet per minute or standard cubic feet per minute? You just don't know. And so you have to clarify which one it is that you're using. And the actual cubic feet per minute, that's going to change all throughout the system with compressible flow systems. So volumetric flow parameters may not be the best to work with when you're dealing with gas flow. I do know that people still like to use them a lot, so at least having an understanding of what's what will help in that particular situation. So again, your densities change, your velocities change, your volumetric flow rate is also going to change. So if you said that I had 100 cubic feet per minute in a pipe, that doesn't really mean anything because it's going to change from the inlet to the outlet. And so they may stay relatively constant for low velocity systems, small pressure losses, and constant temperatures. And how much are they going to change? Well, that's where you have to actually compare doing a simplified analysis with like fathom with a actual thermodynamic analysis with Aero. So let's see if I can hide my taskbar. No, I'm trying to get rid of my taskbar. looks like it's not going to do it. This is where I talked about standard cubic feet per minute. Again, I mentioned this earlier where this is going to tie a volumetric quantity to a specific density at standard temperature and pressure. So this is constant and it's really considered a mass flow rate quantity. So if you were using AFT Aero, here are different parameters that you could add. So here on my pipes tab, these are all the volumetric flow quantities. I've got the standard cubic feet per minute. So with this one, if you want to use this unit, standard cubic feet per minute, you're not going to look at volumetric flow quantities. You're going to need to look at that as a mass flow rate quantity. This goes the same for if you're specifying a fixed flow on your fan. So right here, if you want to use standard cubic feet per minute, if I use volumetric flow, there is no SCFM. All you see is cubic feet per minute. But again, which quantity is that? Actual or standard or something different? We don't know. So if you want to use standard, you have to choose mass flow rate. And then here's where you can find the normal cubic whatevers. And here's the standard cubic feet per minute. So that's how you find the standard and normal volumetric quantities, is by choosing mass flow rate. And then you can pick the appropriate units. So here we've got mass flow, but that's standard cubic feet per minute. And then I've got the volumetric flow rate at the inlet of the pipe, volumetric flow rate at the outlet of the pipe, and both of these are cubic feet per minute. And then I've got the average. And we want to compare these with AFT Fathom. Fathom, that only is going to give you volumetric flow rate, and it's it's not even really, average. It's a constant value because Fathom is assuming constant densities. So here's our breakdown in, here's what I did to get this data out easily. Let me show you how to do a control or an output control format. So for the output window, when we populate this, there is a default list of parameters that you can, that Aero and Fathom are going to show you. So if I was to choose Aero default, it's a whole different list of parameters, and I may not care about all these parameters. I might care about some different ones. So I can add and remove parameters, reorder them, change units as I desire. Once I get it set up how I want, I would save it as a control format and give it a name. Well, you can then use that control format file for any Aero model. And I already set that up. So what I want to do is I want to load my control format file. So this is the one that I previously had before I clicked the Aero default button. So as you can see, it's got mass flow, average velocity, inlet and outlet pressure for stagnation and static, etc. But there's a different one that I made, including the special volumetric flow rate quantities that I wanted to compare. So I can click on load control format, and this is going to be the Fathom to Aero comparison using Aero with volumetric. That's just what I named it. So now I've got what I want, mass flow rate in pounds per second. I also have mass flow rate in standard cubic feet per minute. So that's nice. We can do the same parameter multiple times with different units. You don't have to do any extra calculations in Excel to get that. Just add it multiple times and you're done. I have the volumetric flow rate average. I did not keep the inlet and outlet volumetric flow rates from Aero in here. Okay, so here's where you can see inlet and outlet volumetric flow rate. I just left those off because really I care about comparing this with Fathom. So this is what I imported or these are my control formats for Aero, and then Fathom, I have something similar. So here in Fathom, when I load my control format, it's this guy, Fathom with volumetric. So for Fathom parameters, as you can see, there's only one volumetric quantity, and that's just volumetric flow rate. So you don't have as fine of resolution when you're dealing with incompressible flow. All right, after I got all that data into my Excel spreadsheet, here's all my volumetric flows. So I've got my standard cubic feet per minute, and then I have the average volumetric flow rate. Both of those are from Aero. And then I have the volumetric flow rate from Fathom. And again, I've got the two different scenarios that I'm comparing. So here are the results for the 80% efficient scenario for the blower. As you can see here, there are some slight differences in some pipes where things are relatively close. In other pipes, look at this. The average volumetric flow rate for Aero is very different than the Fathom volumetric flow rate. Okay, and so you see that in several of these pipes. But here they are very similar. Here they're very similar, and you've got those differences. So it looks like when you're dealing with AFT Fathom, keep this in mind that when looking at incompressible flow, typically, if that's what you're comparing, or if that's what you're dealing with, Fathom is going to be over predicting the volumetric flow rate, the actual volumetric flow rate. So, which is really meaningless in Fathom because again, it's changing. So here, all you have is the average. So these are the differences for the 80% scenario, and these are the differences in the 60% efficient scenario. So when I switch between these two scenarios and you look at the red bars for Fathom, you can see how the efficiency of the blower makes no difference in results in Fathom. Okay, it only makes a difference in results in Aero because of the efficiency having an impact on your temperatures. Your temperatures then have an impact on your thermophysical properties, which then has an impact on your volumetric flow rates. So they're different. You're just going to have to, be able to know how to deal with that. With Fathom, you're always going to have a level of uncertainty versus in Aero, you can know exactly what it is. All right, now let's take a look at some comparisons of a flow path. So here there are several flow paths that are in this system. You can go from the atmospheric intake out to each of these rooms. You can do another flow path. You can do another flow path. You should look at all of those. I'm only looking at one of them. And this may or may not be the hydraulically most remote room. It kind of looked like it was, so I just went with it. So in this flow path, I'm looking at pressure, temperature, and velocity. So if I go back into Aero, the way that you can do that easily is by creating a group. So if I select a group, did I already make it for this one? Let's see. No. So here's how you make a group to compare different paths. So I'm going to select my pipes along a flow path here. And then I'm going to grab, oops, I forgot to hold the control key down. So I'm going to hold the control key and then do that. As you can see, I missed one of the branch junctions. That's not necessary. You do not have to select junctions when you are establishing a flow path for graphing. You only need to have the pipes in a continuous flow path. So I'm going to go to Edit, Groups, Create. I'm going to call this Path to room A3. And so this has my pipes for that group and junctions, but again, it doesn't care for your junctions. If you're doing a profile plot, that's fine. And we'll click OK. And then on the graph results here, I already set up my profile. So if I did profile and then plot multiple paths using groups, here's if I did individual paths to all the other rooms, this is where you would find them, and you can plot them together. So that's nice. And so I looked at pressure, and then I added a second parameter for temperature and a third parameter for velocity. And rather than having to set this up every single time, I already did that with this graph list item that I already filed away from before. So here's what we're getting in Aero. I did the same thing in Fathom, where I created that same graph list item. And I'm just trying to plot it. Plot for me, come on. There you go. So there's the Fathom results. I clicked on this button to copy the XY data, and I threw it into my Excel spreadsheet. And so that's where I have my results. So let's take a look at this. So here's the pressure profile comparison. So one thing that I want to mention is that you can only see 3 lines, even though 4 of them are plotted. Well, it just so happens that the pressure profile for the Fathom results, 80% versus 60% efficiency on the blower, are exactly the same. So the blower efficiency has no impact on your pressure results in Fathom. And so here we can see that Aero is the blue and red results, and Aero is predicting some higher pressures than Fathom does as you travel down the flow path. So that could be good or bad depending on if you have pressure sensitive equipment. Maybe you might need more pressure and you're not getting enough if you were only using Fathom. So if you needed as much pressure as you can get, Fathom's not going to give you the right answers. Aero tells you exactly what you're getting, and so it will also account for the impact on your blower efficiencies. So there's your differences. Now, they're not huge in this situation. The scale is fairly small, so it's not very big differences for this particular application, but I'm only looking at this flow path. Maybe there are some bigger differences on this flow path. You only know when you look at it. So that's what I have for pressure. Give me 1 second. Okay. Now here are the temperature results for the different flow paths. So again, as you can see in Fathom, the results are right on top of each other. No differences in results for blower efficiency in Fathom. It doesn't touch it. And the temperatures are exactly the same because Fathom does not do heat transfer with gases. Fathom can do heat transfer with liquids, but not with gases. And so here, even if you were to use an Aero adiabatic pipes, which I think it does, let me check. So here's Aero. If I open up this particular pipe, what I had, this is adiabatic, so perfectly insulated, no heat losses. So as you can see with compressible flow, you're still going to deal with temperature change. And you're not going to see that at all in Fathom. And so in Fathom, you're going to be seeing 70 degrees coming out at all of the pipes into the room versus here you can clearly see that when you're discharging into that room A3, man, those are some really high temperatures. If you're trying to do some heating, man, this is really heating things up where you're dumping in 230 degrees into the room for a 60% efficient blower. And it's significantly different if you have better efficiency. So that is important to pay attention to, and that's a reason why you would need to use AFT Aero for this, to get the right temperatures. And then here's our velocities. So as you can see in Fathom, constant velocities. All you're seeing is the different step changes where you have your various flow splits and whatnot. And then you can see how in Aero, as it starts to get to the outlet, this is where you have a non-linear increase in flow. So if that pipe was longer, you might see some sonic choking potentially where you have really high velocities. And so that might be an issue. You know, if you're only looking at Fathom, you're seeing, okay, I'm going to be getting 220 feet per second, where in reality, if you have a 60% efficient blower, you're actually going to be seeing 280 feet per second coming out of that outlet. And so that's going to be blowing a lot faster and may not be good. So Aero is just going to track the exact velocity values throughout your entire flow path. Now, let's see here. What you could do is, if you want to look at volumetric flow rate for Aero, we could go to the graph results window, and this would be another plot that we could do where I've got all those pipes, and I'm actually going to just do one for volumetric flow rate, and we'll do cubic feet per minute. And so this will show you how your volumetric flow rate changes throughout the system. This could be another thing that you can plot in comparison to Fathom. So here's Aero's volumetric flow rate versus my flow path, and then I'll do Fathom as well. So and then we can copy the data for both of them, and we can paste them together. So we're going from 0 to 30, and as you can see here, well, I had different units. That's cubic feet per second. We'll do cubic feet per minute. There we go. 0 to 2,000, and we got 0 to 2,000. And so that's where you can see some slight differences. So this might be another parameter that you would want to look at as a flow path, not just doing, you might not just want to do your comparison side by side like this. It might be more fruitful for you if you do a flow path comparison of the volumetric flow rates as well. That would give you a better picture of your differences in results. And I would show, here are the pipes where incompressible flow assumptions are okay, and here are the pipes that it's not. So just to summarize, the mass flow rates are virtually identical between Aero and Fathom. Need to distinguish between different volumetric flow rate parameters, actual versus average versus standard. Sometimes they might be close, sometimes they might be different. AFT Aero is always going to give you the most trustworthy and more accurate results. Aero is accounting for blower efficiencies and compression thermodynamics. You're not going to see an impact of that in Fathom, but you will see an impact of that in Aero. And it showed that the pressures were close for this specific system. Compression heating is significant. Fathom only considers constant temperatures, and then your velocities are correctly calculated in Aero, and there you go. So that's what you would do if you are, let's say that you're a Fathom user, okay? If you're a Fathom user and You've been using it for gas piping systems all this time. And now you are curious, hey, how are my results from Fathom going to compare with the actual accurate results that I would see in AFT Aero? Well, if you don't have both Fathom and Aero, feel free to contact me and I'll be happy to help you look at this. Um, we can set up a evaluation license for you where you can try out AFT Aero for a couple of weeks and you can do exactly what I did, where take your Fathom model into Aero and run both of your models side by side and then compare the results side by side like how I did, where you're looking at, your flow rates for both mass flow and volumetric, your profile plots, temperatures, velocities, pressures, etc. And that would tell you in your specific application, are you okay with using Fathom or not? Now, this is kind of like a one-time deal. We're not going to just set up something where every single time you're dealing with a gas system in Fathom that will turn on an evaluation license for you. If you have several systems that you want to evaluate and you already have a license of Fathom, maybe purchase a short-term lease of Aero. That way, you can get it for a lower price with a quarterly lease, and that way you can have a little bit more time to better evaluate your results to see what those differences are. All right. Now, how about a steam system? So this is just another example that comes from the AFT Aero help file. So if I go to the help menu again in Aero, show examples, and pick my desired units, I'm looking at the process steam system. Okay, so that's what I'm going to be looking at there. And we're going to look at the same kind of results. So let me go ahead and open that model up. So file open. No, I'm not going to save that. And then here's my steam system. All right. Now, I already prepared this for Fathom as well, so I'm not going to demonstrate importing it. Just note here that I'm using, I decided to make a slight deviation from the walkthrough tutorial, and I'm using more accurate steam. So I'm using the ASME steam tables for my fluid properties. And keep in mind, Aero is using a tank junction, but really, there's nothing special about it. All it is a fixed pressure and temperature. So give me 1 second. Sorry about that. Been talking a lot. Had to rehydrate. Okay. So we've got, okay, so time is, right now we're at an hour. I've got a few more minutes that I'm going to go through and show the results. Again, this webinar is being recorded. So if you are listening live and you need to head out, feel free to do so. Feel free to keep listening in if you're able to. And then when you're listening to the recording, just start at about an hour into it, and then you can watch the rest of the show. Okay, so here I've got Aero, and then I'm going to open up the Fathom model. And here's my steam system for Fathom. And as you can see for my boilers, same thing. I already changed those to assign pressure junctions 300 psi. Where does the temperature go? It goes in the system properties window. So here, when I choose ASME steam, I chose gas and then pressure and temperature. So at 300 psia, this is where I can do 800 degrees Fahrenheit. But again, it's going to use constant properties, and they're not going to change in Fathom where they will in Aero. So here we have some relatively high flow rates. And so I'm not going to do a deep comparison of things, but you'll see how the flow rates change for each of the users. So they're not exactly the same for every single user. Now, I already ran my result, or I already ran the models and got the results. So here are my Excel results here. So I've got my Aero results and my Fathom results. And what I also did was I calculated absolute differences between Fathom and Aero. I simply subtracted the Fathom results from Aero to see what those differences were. As you can see, for some of these pressure drops, they're significant. And then here's my percent differences between Fathom and Aero. All right, and then let's take a look at the flows first. So here are my flow rate comparisons for mass flow. As you can see, they're very similar, again, between Fathom and Aero for my steam system. But here's a really important reason why. It's because I'm using fixed flow rates. So obviously, if I'm fixing the flow rates at all of the outlet locations there like this, then yes, we're going to expect the results to be virtually identical between Fathom and Aero. So what would you do? Well, check the pressures at the assigned flow junctions between Fathom and Aero, because that's where you might see some big differences. Let's do it. So here's how we can set this up. So I'm going to modify my output control, and I'm going to look at my assigned flow, and I'm going to make this a little bit more simplified. So for my junctions, I'm going to take off pressure drop, and I'm only going to show the inlet pressure. All these other things I don't care about, because when you're dealing with looking at the results, it's better to look at the results in the pipes themselves, because, you know, what does the inlet and outlet mean for an assigned flow junction? Nothing. So it's helpful if you just look at the pressure or a single pressure value at the assigned flow. So here I've got my mass flow. I can also set up my mass flow one more time in terms of, let's see, pounds per hour. Okay, so I've got my mass flow in pounds per hour, standard cubic feet per minute. I'm going to get rid of that because Fathom does not use standard cubic feet per minute. I could compare volumetric, but I'm not going to deal with that on the junctions. All right, and I've got my pressure. So this is stagnation pressure. This is static pressure. And for Fathom, we'll do the same thing. So here's my junction results, and I'm going to take off the outlet and some of these other things. Put that up here. Make this be pounds mass per hour. All right. There we go. Okay, so let's take a look at this. Here are my Aero results, and here are my Fathom results. So the pressures at the outlets are very different from what Fathom is giving you. So here, you're going to see much higher pressures for fathom than you do in Aero, and this is going to make an impact on things. So this is where you're going to see some very large differences, and where Aero is going to give you much more accurate results. So that's just what I wanted to show quickly, because I didn't throw that into the presentation. And that's where you got a big differences in results, because again, if you're only looking at flow rates, they're virtually the same. But what's different? The pressures at the assigned flow junctions. Here's my volumetric flow rate comparisons. This includes the standard cubic feet per minute for Aero. As you can see, they are wildly different than what you're seeing for average volumetric flow rate in Aero versus what you would see in Fathom. So this is pipe number on the bottom. I did two separate plots. This is including the standard cubic feet per minute. This does not. So even when you're not comparing standard cubic feet per minute, if you're only looking at the average volumetric flow rate in Aero versus Fathom, you do have some very different results in some of these pipes. So this is where you're going to want to use AFT Aero. It's going to give you more accuracy. If I did a flow path comparison of results, one second. If I did a flow path comparison results, this is what I'm looking at from the boiler number 1 all the way to user number 6. And again, you'd also want to do a flow path for all of the other legs if you were doing a full-on analysis. Here's my pressure profile. So as you can see, the pressures in Fathom are much more over-predicted than Aero. So here we're seeing about 215 or so versus 185. So as you flow down the flow path, you're seeing more differences due to the compressibility of the gas. In this particular system, Aero is modeling heat transfer. That is a part of this analysis. So if I was to go to the model data window and we look at the pipes, you can see here that we are doing convective heat transfer. The ambient temperatures are 75 degrees Fahrenheit, so we are getting some cooling from the boilers all the way to the outlet. Fathom cannot do that. Fathom is assuming constant temperatures. So this is where we're going to have a big difference between Fathom and Aero. And so here, you're going to see some very different results in terms of temperature. So that's something to keep in mind. Temperatures can also affect your flow rates. So if you see different temperatures, that can heat transfer can have an impact on your flow rates and pressures as well. Sometimes it's small, but other times it might be fairly large. So you got to look at it with an accurate solution to know, is your incompressible flow methods good enough? And then lastly, here is the velocity profile. So here we have higher pressure, we have really high pressure and temperature steam coming in. Again, we have 300 psia, 800 degrees Fahrenheit. That's pretty high pressure and temperature. So we might see some areas where you might be sonically choked potentially. And so we've got a very significant increase in velocity in some of these areas, and that's not being dealt with in Fathom. So this is another reason why it's important to use AFT Aero to know what the velocity actually is. Here we're at about 425 versus 300. That could be a big difference. That's important. All right. So those are the result comparisons. You can also look at the volumetric flow rate change. So if I was to set that up really quick, I'll just do my group that I already created and look at volumetric flow rate. There's cubic feet per minute. So here's what we see for that. And then if I was to do the same thing for fathom, here's my group. Make this be cubic feet per minute. This is just another comparison that I would use to try and see what the differences are in results. So that's pretty big differences right there. So here in Aero, this is actual volumetric flow rate. Why is this actual? Well, the reason why is because it's actually correctly tracking what the volumetric flow rate is at each station along the pipe. So if you're doing a profile plot for volumetric flow in Aero, this is going to be correct. That will give you more realistic results when you're looking at volumetric flow rates, because I can know if exactly what my volumetric flow rate is all throughout the pipeline. And this is a very different graph than what we're seeing in Fathom, as you can see. All right. Well, thank you all very much for your time today and for listening in. And again, feel free to email me, and I'll be happy to send you the presentation. Here's my email address for you, and we'll get that sent over. You'll be sent a link later this week if you're listening live. If you're listening to the recording, thank you for joining us. And again, if you ever want to try out AFT Aero and compare that to Fathom, let us know. We'll be happy to set up that evaluation for you. All right. Thanks again, everyone. Take care and have a wonderful week.